Welcome back to another video lecture. In this lecture, we're going to cover section 2.9 on sampling distributions and the central limit theorem. Fair warning, I think this will be a little bit lengthier than a usual lecture. I haven't recorded it yet, of course, but I anticipate it's going to be a little bit on the long side. That said, it's going to contain a lot of really, I think, interesting information and very useful information. This is what we have been building up to in this unit because this section contains the kinds of probabilities that we actually really need in order to perform inference in Unit 3. So let's dig in. The sampling distributions that we're going to discuss in this section are the sampling distribution of the sample mean and the sampling distribution of the sample proportion. So let's talk about each of those. The sampling distribution of the sample mean is the probability distribution of all possible values of x bar. For example, let's say that the government wants to determine the mean of all U.S. household incomes, right? What they might do is take a survey of some U.S. households. Now, not everyone in the population is going to get surveyed, right? So you're going to have different samples of individuals, and each sample is going to have its own sample mean, and those sample means might not be exactly the same thing. In fact, they won't be, right? Some sample means might be overestimates, and some of them might be underestimates, right? But the idea is that, okay, if x bar changes from one sample to the next, then x bar itself is a random variable. And just like the random variables from the previous sections that we've been looking at, we can make a probability distribution and a probability histogram for x bar. When we do so, we observe the following facts, right? So suppose that a simple random sample of size n is drawn from a population with mean mu and standard deviation sigma. The mean of the sampling distribution of x bar, mu sub x bar, right, is equal to mu. I know that sounds really convoluted, but let's think about this for a second with a concrete example, right? So going back to this U.S. household income thing, if we took all of the possible sample means from all of the different possible samples, and then we wanted to know, well, what's the average sample mean? In other words, if we took the mean of the sample means, mu sub x bar, what would that be? Well, some of these sample means, as we've said a second ago, are going to overestimate the true population mean, and some of them are going to underestimate it. But when we take the average of all possible sample means, right, mu sub x bar, then the overestimates will counterbalance the underestimates, and we should end up dead on equal to whatever the actual population mean is for U.S. household incomes. That's what the central limit theorem predicts, okay, for the mean of the sample means. For the standard deviation of the sample means, we have a similar statement, okay? The standard deviation of the sample means is going to be equal to the population mean divided by the square root of whatever our sample size was, okay? That one I think is a little bit more opaque, but if you bear with me, we'll run some simulations here in a few minutes to kind of convince ourselves that that's a true fact, okay? And then the third thing that we want to take note of is the shape of the distribution, right? We've considered the center and the spread. Now the shape of the distribution of x bar, in other words, if we took all possible sample means and we made a histogram out of them, what shape would that histogram be? And the answer is the shape of that histogram would be approximately normal, okay, provided that the underlying population from which the sample is drawn is normal, or that n is sufficiently large. And by sufficiently large, we mean more than 30. Usually more than 30 is sufficiently large. So, okay. Here's the moral of that story, right? The moral of the story is, if we want to compute a probability involving a single observation of a normal variable, then we just use the normal distribution, right, in Desmos, okay, like we did in 2.7. But if we want to compute a probability involving a sample mean of multiple observations. The good news is that we can still use that normal distribution, and the only thing we need to do is change our standard deviation. So instead of putting in the population standard deviation by itself, we would put in sigma divided by the square root of n. So it's really kind of a fascinating thing and very, very useful for us. Let me give you a couple examples. Number one says, the heights of women are normally distributed with mu equals 63.6 inches and sigma equals 2.3 inches. Part A asks, if a woman is selected at random, what is the probability that her height is more than 64 inches? Well, we're told that the heights of women are normally distributed, and we're just looking in part A for the probability of that one woman is more than 64 inches tall. Well, this is no different than what we did in 2.7, right? This is just a 2.7 problem. And so to calculate this probability, we would use the normal distribution. Our mean is 63.6, and our standard deviation is 2.3. So we'll use the normal distribution with that mean and standard deviation. Okay, and then the probability that we're looking for is the probability that x is more than 64, right? We want to know what's the probability that she's more than 64 inches tall. So to compute that probability, our minimum value will be 64. And we won't have a maximum value, so we'll just put infinity, INFTY, for the maximum value. Okay, let's see what we get. We've done these kinds of probabilities before. We've got 63.6 and 2.3. And let me zoom in on that. Okay, and we'll find the cumulative probability. We wanted the probability that she was more than 64 inches tall. So we'll put in 64 for the min and leave the max at infinity. And rounding to 4 decimal places, this would be approximately 0.4310. Okay, so that's how that one works. Nothing new there. But now look at part B. It says, if 10 women are randomly selected, what is the probability that their mean height is more than 64 inches? Okay, so we're asked to compute a probability involving a sample mean, right? We want the probability that x bar is more than 64 inches. So that's a little bit different, right? And if we hadn't had those facts in this gray box up here, we wouldn't really know what to do. But we do have these facts. We know that since x is normally distributed, x bar is also going to be normally distributed. So we can use the normal calculator. And this is the mean that we should use in the normal calculator, and this is the standard deviation that we should use. So let's write those down. Okay, the mean we're going to use mu sub x bar. Well, that's just the population mean, which is 63.6. The standard deviation that we should use is the population standard deviation divided by the square root of our sample size. That would be 2.3 divided by the square root of 10, because we have a sample of 10 women, right, in this case. So you pop that into your calculator, and let's round this to 2 decimal places. 2.3 divided by square root of 10 is approximately 0.73. So to compute this probability here, we're going to use the normal distribution. With a mean of 63.6 and a standard deviation of 0.73. We'll set the minimum at 64, right, since we want the probability that the mean is greater than 64, and no maximum, right? max is just infinity. Notice that the only difference between these problems is the standard deviation that we're using, right? This is the only difference, okay? Here, we just had to divide by the square root of n. Let's see what we get. So I'm going to change the standard deviation to 0.73. Ooh, and let me zoom. Okay. And there we go. The probability is 0.2919 approximately. Okay. Notice that the probability decreased, and this should make some sense to us because the population mean height was 63.6, and 64 is a little bit more than that. So, but it's not that much more than that, right? So if you're just talking about one woman, there's a pretty high likelihood that she's going to be more than 64 inches tall. But if you're talking about 10 women, right, you're talking about the sample mean of 10 women, well, then it's a little bit less likely, isn't it, that their sample mean is going to be more than 64 inches when the population mean is only 63.6. So I think these answers make sense. By the way, this is a 2.9 problem. Okay, so part A was a 2.7 problem, nothing new. 2.9 is the new stuff that we're saying. We're saying, hey, look, we can calculate probabilities involving sample means now. Okay, that's going to be incredibly useful. Okay. On example 2 here, I just want to run through a few different scenarios to show you when it is appropriate to use the normal distribution to calculate probabilities involving x bar and when it's not appropriate to do so. So let's take a look, right? Part A says, cars arrive at a Burger King's drive-through uniformly at the rate of 20 cars per hour, or 20 cars every hour between 1 and 2 p.m. Note that if x is the number of cars that arrive between 1 and 2 p.m., then x is a Poisson random variable. Okay? A sample of 10 days is taken, and the number of cars that arrive between 1 and 2 p.m. is recorded. Let x bar be the sample mean number of arrivals on this 10-day sample. Okay? Describe the sampling distribution of x bar. And then follow-up question, why does the central limit theorem not help us determine the shape of the distribution of x bar in this particular case? Well, so let's do this. When we're asked to describe the sampling distribution of x bar, what we're being asked to do is to give the shape, center, and spread of the distribution, just like we've been doing with probability distributions and with data sets all semester, right? So we want to give the shape, center, and spread. We'll talk about the shape in a second. As far as the center is concerned, well, it would just be the mean of our sample means, mu sub x bar. And we know from the central limit theorem that this is just equal to mu. Now for a Poisson distribution, mu is equal to lambda times t, okay, where lambda is in this case, it would be the number of arrivals in a 1 hour period, and t is the number of hours, right? In this case, we're only talking about a 1 hour period between 1 and 2 p.m., and we know that 20 cars arrive between 1 and 2 p.m., so it would just be 20, right? It would be 20 times 1, which is just 20, right? So that's the center of our distribution. As far as the spread of the distribution is concerned, we would use sigma sub x bar, right? Sigma sub x bar is going to be sigma divided by the square root of n. Now, we should do a little bit of scratch work, I guess, to figure out what sigma is. For a Poisson distribution, sigma is the square root of your mean, right? 20 in this case. So this would just be square root of 20 divided by square root of 10, since our sample size is 10 days, right? 10 days. So you can punch that into your calculator and see what you get. This should come out to approximately 1.4 or 1.41 if you want to go to 2 decimal places. So there's our center and spread. Let me double check that. I did that math in my head and I want to make sure. Yeah, 1.41, square root of 2. Okay, so there's our center, there's our spread. As far as the shape of the distribution is concerned, there we would just have to leave a question mark, okay? We would have to leave a question mark because the population that we're drawing our samples from is not normally distributed. It's a Poisson distribution, right? It's not a normal distribution, it's a Poisson distribution. That's okay as long as our sample size is large, okay? It's okay as long as we have a sample size of at least 30. But we don't have a sample size of at least 30. We have a sample size of 10. So we would have to say the shape of x bar is unknown because x is Poisson, not normal, and n is less than 30. And this is why the central limit theorem doesn't help us determine what the shape of the distribution of x bar would be in this case, okay? So that's part A. Now, if you were asked in part A to compute some probabilities involving x bar, you would not be able to use the normal distribution to do it because we don't know if x bar is normally distributed, okay? But now let's contrast that with part B. It says cars arrive at a Burger King's drive-thru uniformly at the rate of 20 cars per hour, or 20 cars every hour between 1 and 2 p.m. Note that if x is the number of cars, then x is a Poisson variable. A sample of 40 days is taken, and the number of cars that arrive between 1 and 2 p.m. is recorded. Let x bar be the sample mean number of arrivals on this 40-day sample, and describe the sampling distribution of x bar. And then we're asked a follow-up question. Why may we conclude that x bar is normally distributed in this case, even though x is not uniform, it's Poisson. Even though x is Poisson. I'll change that in the notes before I post this lecture. Well, okay, we'll do the same thing, right? We're going to describe the center. Mu sub x bar equals mu. And we already talked about the fact that that's 20, okay? 20 cars per hour. So in a 1 hour period, on average, we expect 20 cars to arrive. Okay? Spread. Sigma sub x bar is sigma divided by square root of n. We already talked about that, the fact that for a Poisson distribution, sigma is the square root of mu, okay? Mu being 20 in this case. So sigma would be the square root of 20. And n is 40 in this case. So we would divide square root of 20 by square root of 40. And that comes out to about 0.71. So we've got the shape, or the center of our distribution and the spread of our distribution. Now, as far as the shape is concerned, note that the central limit theorem says that regardless of the underlying population, as long as our sample size is more than 30, x bar will be normally distributed. And so we'll conclude for the shape that x bar is normally distributed since n is greater than or equal to 30. Okay? It doesn't matter that x was not normal, right? We'll say even though x is Poisson, right? Not normal. We can still nevertheless conclude that x bar is normally distributed. Okay, part C. Different scenario this time. It says the reading rates of second grade students is approximately normal with a mean of 90 words per minute and a standard deviation of 10 words per minute. A sample of 10 second graders is taken. Describe the sampling distribution of x bar, which is the mean reading speed of the 10 students. And then we're asked, why may we conclude that x bar is normal in this case, even though we have a small sample size? Okay, so same thing here. Center mu sub x bar equals mu. We're told just point blank that the mean reading speed is 90 words per minute. Okay. Spread is going to be sigma sub x bar. That's sigma divided by the square root of n. We're told point blank that the standard deviation is 10 words per minute. So sigma equals 10. And our sample size is also 10 in this case. So we're going to divide by the square root of 10. Okay. So let's see what we get there. That comes out to about 3.16 if we round to 2 decimal places. So we've got our center and we've got our spread. Now the shape. Well, it's true that n is only 10, which is less than 30. However, we were told that the reading rates are normally distributed. In other words, the population that we're drawing from is itself normally distributed, and therefore x bar will be normally distributed. Okay, so we'll say x bar is normally distributed since x is normally distributed. Right? We could just call it normal. We'll say x bar is normally distributed since x is normal. Even though our sample size is small and less than 30. So x bar is going to be normally distributed as long as we either have a large sample size, as was the case in part B, or the population that we're drawing from is normal, as was the case in part C. The only way that x bar fails to be normally distributed is if both of those conditions are not met, as was the case in part A. Okay, let's look at another example. This time maybe a little bit not quite as highfalutin. We'll just work on crunching some probabilities. Number 3 here says, the length of human pregnancies is approximately normally distributed with mean 266 days and standard deviation 16 days. Part A asks, what's the probability a randomly selected pregnancy lasts less than 260 days? Well, since the lengths of pregnancies are normally distributed, we can use the normal distribution to compute this probability. Mean, we're told, is 266. Sigma, we're told, is 16. So we're going to use the normal distribution with mean 266 and standard deviation 16. And to compute the probability that a randomly selected pregnancy X is less than 260. To compute that probability, we won't have a minimum value. Okay, we'll just say negative infinity. And for our maximum value, we'll put in 260. Okay, so let's see what we get. 266 and 16. (266, 16). Let me zoom in. Okay, we want negative infinity here, and 60 there because we were looking, or 260, sorry, because we were looking for the probability that a randomly selected pregnancy lasted less than 260 days. So it looks like there's about a 35% chance of that happening, right? 0.3538. Whoops. 0.3538. Okay, now part B. What's the probability that a randomly selected sample of 20 pregnancies has a mean gestation period of 260 days or less? So this time we're looking for the probability X bar is less than 260. So we can use the normal calculator here, even though we have a small sample size, because we know that pregnancies are normally distributed, okay? So X bar will be normally distributed. So we can use the normal distribution. When we do, we're going to need to enter something for the mean, mu sub X bar in this case. But mu sub X bar is just the same thing as mu, okay, which is 266. We'll also need to enter something for the standard deviation. We're going to want to enter sigma sub X bar, which is sigma divided by square root of n. Sigma, we were told, was 16, and n in this case is 20, right? It's a random sample of 20 pregnancies. So we'll do 16 divided by square root of 20. Let's round that to 2 decimal places. It's approximately 3.58. And then to compute this probability, we'll enter a minimum of negative infinity, just like before, and a maximum of 260, just like before. So the only thing that changes is the standard deviation, right? That's the only thing that changes. Oh, I didn't write down the normal distribution. Let me amend that. We'll use the normal distribution with a mean of 266 and a standard deviation of 3.58. Okay, a minimum of negative infinity and a maximum of 260. Okay, so yes, the only thing that changes is what I've circled in blue there. So let's change the standard deviation to 3.58 and see what we get. And we'll zoom in again. All right, so the probability shrank. So we have 0.0469 approximately, 0.0469. Okay, so while there's about a 35% chance of one randomly selected pregnancy lasting less than 260 days, there's only about a 5% chance of a sample of 20 pregnancies having a mean that's less than 260 days. Okay, well, let's look at part C. It says, what is the probability that a random sample of 50 pregnancies has a mean gestation of 260 days or less? Okay, well, same deal, right? Mu sub X bar is still going to be 266. Sigma sub X bar is still sigma divided by square root of n, but n has changed, right? Sigma is 16, n is now 50. So rounding that to 2 decimal places, 16 divided by square root of 50 is approximately 2.26. 2.26. So now that's changed, okay? But we're still going to use the normal distribution. This time we can use the normal distribution on 2 counts. First of all, because pregnancies are normally distributed, but second of all, because even if they weren't, our sample size is big enough that we'd be able to use the normal distribution for sure. Okay, so we're going to use the normal distribution with a mean of 266 and a standard deviation of 2.26. And for the minimum, we're still going to put in negative infinity And for the maximum, we're going to put in 260. Okay, probability that x bar is less than 260 is approximately, let's see, we'll change the standard deviation to 2.26. So that comes out to 0.0040 if we round to 4 decimal places. Okay, so once again, the probability decreased. So now part D asks a follow-up question. It says, suppose that the women in your random sample of 50 pregnancies had all been exposed to glycol ethers during their pregnancy. What might you conclude if the mean gestation period was 260 days or less? Well, we just computed the probability of that happening. Remember that in general, the average gestation period is 266 days. But if we have a sample of 50 women whose average pregnancy lasts less than 260 days, so it's like almost a full week shorter, that's very unusual, right? 0.0040 is much less than 5%. It's less than 1%, right? So it's very unusual. So then you would have to ask yourself, well, what might account for the fact that we observed something so unusual? And well, it could be because they were all exposed to glycol ethers. Glycol ethers, by the way, they're in cleaning products. Some cleaning products, not all, obviously. But what might we conclude? Well, we might conclude that being exposed to glycol ethers it causes a shorter gestation period, which could be bad because that means that your baby might be born premature, right? So we might conclude, that exposure to glycol ethers may lead to a shorter gestation period. Right? Which would be bad. I think would be bad, right? Because then your baby's going to be born premature. So if you're pregnant, steer clear of glycol ethers would be the recommendation, right? Okay. So you can kind of see why it would be so important for us to be able to compute probabilities involving sample means. This is the way that we learn about things in the real world. You know, we run some kind of experiment, and then based on the results of that, or we do some kind of observational study, right? But based on what we observe, you know, we can make all kinds of we can compute some probabilities, right, like this, and then come to some decisions that affect the real world. Okay. What I want to do next is just give you a kind of, not really a full-blown proof, but just sort of, I want to run some simulations, okay, to kind of convince you that the facts that we discussed in the gray box on page 1, the central limit theorem for x bar, I want to try to convince us that this is true by running some simulations. So this first one says, scores on an IQ test are normally distributed with a mean score of 100 and a standard deviation of 15. Use technology to help you describe the sampling distribution of the sample mean x bar by simulating the collection of 1,000 samples of size 9 and then later of size 25. So let me show you these simulations. So I'm using a little tool here called StatCrunch to do this. Not simulations. I want sampling distributions. I want to run a bell-shaped simulation with a mean of 100 and a standard deviation of 15. Okay. So the way that this simulation is set up, the distribution at the top that's in gray is the population that we're supposed to be drawing our samples from, okay? As you can see, that population has a mean of 100 and a standard deviation of 15. Now we can simulate taking a sample of size 9, okay? One sample of size 9. So it's doing this simulation. And then it computes the sample mean and drops the sample mean down to the bottom histogram in green, okay? So that would be if we just did this one time. Now, we could take a different sample of size 9. And that would result in a different sample mean. And we could do this again. And get a different sample mean, and again. Okay, and as we do this more and more and more, so far we've done 4 samples of size 9, right? But if we did this, let's say, 1,000 times, then this is the distribution that we would end up with. As you can see, it is a bell-shaped distribution. Okay? But let's also point out, looking at the chart next to the green distribution where it says sample means, right? So it says the mean of those sample means is 100.2019. So in other words, the mean of the sample means is approximately 100, okay? Which is the same as our population mean that we started with. The standard deviation, it says, is 4.9898. So in other words, approximately 5. Well, the central limit theorem predicts that the standard deviation of our sample means would be the population standard deviation divided by the square root of our sample size. The population standard deviation is 15, and our sample size is 9, right? Square root of 9 is 3, and 15 divided by 3 is 5, which is exactly what this sample mean is, or sample this is exactly what the standard deviation of the sample means is. Okay, so let's make note of that, right? So for samples of size 9, we would say the shape is normal, the center was 100, well, approximately. It wasn't exactly equal to 100, but we'll say it was approximately 100. And the standard deviation, sigma sub x bar, was approximately 5, which happens to equal 15 divided by square root of 9, right? So it seems like the central limit theorem is holding up, at least for samples of size 9. We could do the same thing for samples of size 25. Let's take a look. I'm going to reset this. Let's set our sample size to 25 now. And take one sample of size 25. Oh, it doesn't show the individual collection because there's too many. It would take too long. But if we did this 1,000 times, okay, once again we can see that we get kind of a bell-shaped distribution there. I should have zoomed in from the get-go. Okay, so you get a bell-shaped distribution. Let's think about the mean of the sample means down in green, 99.9254. Okay, so it's approximately 100 still. Remember that these are just simulations, so it's not like perfect, but it's pretty close. The standard deviation is 2.9416, so it's approximately 3. And that checks out, right? Because our sample size was 25. The square root of 25 is 5. Our population standard deviation was 15, and 15 divided by 5 is 3, right? Which is what we're getting for the standard deviation of our sample means. Okay, so central limit theorem seems to be holding up there as well. I'm not going to write anything there, except maybe a big check mark. Central limit theorem seems to be holding up. Okay, but let's change this a little. This next one says, suppose that you have data that is skewed right. Use technology to help you describe the sampling distribution of the sample mean x bar by simulating the collection of 1,000 samples of size 4 and 49. So what the central limit theorem is going to predict is that for a sample of size 4, since our data is not normal, we're not going to get a normal distribution for the sample means, right? It's not going to be bell-shaped. But for n equals 49, it will be bell-shaped. Let's see. Let's see what happens. So I'm going to have to close this and run a different simulation. I want to do sampling distributions. I want a right skewed one this time. Okay, let me zoom in. Okay, so now I've got this right skewed distribution, but otherwise this is set up the same way, okay, as the previous one. I didn't get to choose the mean and the standard deviation here, but that's okay. The mean looks like it's about 14, and the standard deviation looks like it's about 12. Let's make our sample size 4, and we can simulate taking a sample of size 4, one sample of size 4. We could do it again. And again. Okay, and if we did this over and over and over again, this green distribution down at the bottom of the screen, let's see what it looks like if we did it 1,000 times. Okay, or you could do it 10,000 times, right? You could keep clicking 1,000 a bunch of times, and we could get up to 10,000. Looking at the shape of that distribution, it's kind of surprising. It isn't as badly skewed right as what we started with in gray, but it's also not normally distributed. It's definitely got a right tail on there, so it's definitely still skewed to the right. As far as the shape, as far as the center and spread are concerned, though, the mean of our sample means, 13.9491, yeah, that's approximately the same as 14.0519, which is what we started with. The standard deviation is 5.8-ish. Okay, so that's interesting. So standard deviation is about 6 if we round to the nearest whole number. Well, the population standard deviation was about 12, and our sample size was 4. Well, square root of 4 is 2, and 12 divided by 2 is 6, right? So at least as far as the center and spread are concerned, the predictions given by the central limit theorem seem to be holding up here. The only thing is the shape, right, is skewed right. So let's write that down. So the shape is skewed right, but the center and spread are exactly what the central limit theorem predicts, right? Mu sub x bar is still equal to mu, right? It was about 12. And the spread, sigma sub x bar, was still equal to sigma divided by square root of n, right? That was still the case. It was about 6, I think. Okay, let's change, let's run one more simulation. We'll change our sample size to 49 and see what happens if we have a larger sample size. Okay, we can simulate taking 1,000 samples of size 49, and look at that distribution, right? If we do, let's say, 10,000 of them, that's a pretty darn symmetric distribution. That's bell-shaped, okay? Which is really crazy that that ends up happening, but there you go, right? So we get a bell-shaped distribution. So the shape now is bell-shaped. Okay, so that's not a formal proof of the central limit theorem, but I think to me it's convincing, right? It looks like, okay, yeah, it definitely seems like as long as either the underlying population is normally distributed or the sample size is large enough, that x bar will be normally distributed. It'll be bell-shaped, okay? All right, so that's all I have to say about the sampling distribution of the sample mean, at least for now. Let's go ahead and kind of quickly try to talk about the sampling distribution of the sample proportion, okay? It's very similar to the sampling distribution of the sample mean, right? The sampling distribution of the sample mean was the probability distribution of all possible values of x bar. The sampling distribution of the sample proportion is the probability distribution of all possible values of p hat. Okay? And you can see that p hat is going to be a random variable, just like x bar was a random variable, right? Because just like with the sample mean, the sample proportion is likely to differ from one sample to the next. So here's the central limit theorem for the sample proportion p hat. It predicts that the mean of our sample proportions is going to equal our population proportion. And that makes sense, okay? Because some of our sample proportions are going to underestimate the true population proportion, and some of our sample proportions will overestimate the true population proportion. But when we take the average of all of those sample proportions, it should the underestimates should counterbalance the overestimates, and we should end up dead on with the population proportion. So that makes sense. The standard deviation of the sample proportions is going to be sigma sub p hat. It's going to be given by this formula, square root of pq over n, where q is 1 minus p. Just like with the central limit theorem for x bar, I think this formula for sigma sub p hat is a little bit more opaque. It's not as clear why that should be the case, but we can run some simulations to convince us of that. And then finally, and this is the really wild thing in my opinion, the shape of the distribution of p hat. In other words, if you take all of the possible sample proportions and you make a histogram out of them, the shape of that histogram is going to be approximately normally distributed. And this is just crazy because we're starting with something that isn't even continuous. It's a discrete variable. It's binomial, right? And yet, when you collect all of the possible sample proportions, you're going to get a normal distribution out of it, right? So it's really, really wild. But this is true, okay, provided that these two conditions are met. So we'll practice checking those conditions together real quick. Okay. So number 4 says, describe the sampling distribution of p hat if p equals 0.76, n equals 60, and capital N equals 1 million. Okay, so a lowercase n is going to represent our sample size, and an uppercase n is going to represent our population size. And this is kind of a boring example in the sense that we don't really know what the situation here is, but apparently we have a population of 1 million individuals, and we're taking a sample of size 60. And we're being asked to describe the sampling distribution of p hat if the probability of success, whatever that is 76%. Well, as far as the center is concerned, the center of the distribution of the sample proportion p hat is going to be mu sub p hat. And mu sub p hat is just equal to p, which we're told is 0.76. The spread sigma sub p hat is going to be the square root of p times q divided by n. Right? I'm just getting that from this formula right here. Well, p, we're told, is 0.76. Q is 1 minus p. All right, so 1 minus 0.76 would be 0.24. And n is our sample size. We're told n is 60 here. So pop that into your calculator. Make sure that you're taking the square root. In fact, let's do this together just to make sure that we know how to do this right. And I'll show you a common mistake. So give yourself a square root. It should be, and then give yourself a little fraction bar inside the square root. So this should be 0.76 times 0.24 divided by 60. This is the way that you should enter it. A lot of times students will make the mistake of only square rooting the numerator, right? They'll do something like the square root of 0.76 times 0.24 and then divide that by 60. And that's incorrect, okay? The second way is not correct. The square root needs to be over the entire number, not just the numerator, okay? So the correct answer here is 0.055-ish. .055. So we've got the center, we've got the spread. Let's talk about the shape. Well, we know that the shape is going to be normally distributed provided that these two conditions hold. So let's check them. Whoops. I apologize. So let's check those conditions. First condition is that our sample size n, I don't know why I put parentheses there. So let's check those conditions. The first condition is that our sample size n has to be less than or equal to 5% of our population size. So we want to know if this is true. Let's see. Our sample size is 60. Is it true that that's less than or equal to 5% of 1 million? Well, yes. 1% of 1 million is 10,000, so 5% of a million is 50,000. And yeah, 60 is definitely less than or equal to 50,000. So that first condition holds. And I'm going to run out of space, but let's do the second condition. We need to make sure that n times p times q is bigger than or equal to 10. N was 60, p was 0.76, and q was 0.24. So let's see what that equals. 60 times 0.76 times 0.24 comes out to about 10.9. Okay, so this is about 10.9, but that is greater than or equal to 10, so that condition also holds. Since both of those conditions hold, we can conclude, that the shape of the distribution is normally distributed. So p hat is normal. Okay, that's how we describe the sampling distribution of p hat. If one of these conditions here is not met, then it's still the case. This is still true. It's just that we can't conclude that p hat is normally distributed in that circumstance. And so you wouldn't be able to use the normal distribution to compute probabilities involving p hat. But let's take a look at some examples now of applying the central limit theorem for p hat, right? Number 5 here says, according to the National Center for Health Statistics, 15% of all Americans have hearing trouble. In a random sample of 1,250 Americans, what is the probability that at most 13.2% have hearing trouble? Part A asks us to calculate this probability using the binomial distribution, and then part B asks us to calculate the probability using the sampling distribution of p hat. Okay, so for part A, if we're going to use the binomial distribution, then we will go to binomial dist, or we'll type in binomial dist into the calculator. Actually, let me show my work here. For the binomial distribution, we need to know what the sample size is, which in this case 1250. And we also need to know the probability of success, which in this case is 15%. Okay, so we'll use the binomial dist. Whoops. And I think I think it calls for the proportion first and then the sample size. I could be wrong about that. We'll double check it when we go over to Desmos. But we're looking for the probability that at most 13.2% have hearing trouble. And so we'll have to do a little bit of calculation. It's 13.2% of our sample, right? When we're computing a binomial distribution, we're computing a probability about the number of individuals who have success, not the percentage of individuals who have success. And so we have to change this percentage into a number, right? So we'll say, well, X is 13.2%, right? 0.312 of, right, times 1250, right? It's 13.2% of 1250, which comes out to 165. So what we're interested in knowing is the probability that X is at most 165. That would mean X would be less than or equal to 165. Okay, so in the binomial calculator, for our minimum value, we're going to put negative infinity. And for our maximum value, we're going to put 165. Okay, let's see what we get. 15% and 1250. Oh, we put the trials first. Okay, so number of trials, 1250, and then the probability of success, 15. So I apologize, I got that backwards on the notes, but we'll fix it. Let me zoom in. We'll find the cumulative CDF. We can leave the mean at 0 rather than putting in negative infinity. That won't change anything, so you can change the 0 to negative infinity if you want. We want the probability that X is less than or equal to 165. Okay, so we need a 165 there for the maximum value. Okay. And I'm not liking that zoom. I think we can do a little better. Well, we'll lose the top part of the distribution, but just so that I can see that it's shading in the right things. Yeah, that looks about right. We just had a very large sample size, so it's making it look funny. But okay, 0.0390, 0.0390. Approximately. Okay, part B asks us to compute essentially the same probability, but this time using the sampling distribution of p hat. Okay, so let's do it. The sampling distribution of p hat is going to be normally distributed, assuming that these conditions are met, but I'm not going to waste your time checking them. Our sample size is so large, those conditions are going to be met for sure, and you can double check that on your own if you want. But when we use the normal distribution, we need to enter something for the mean, and of course the mean we're going to enter here is mu sub p hat, which is equal to p, which in this case is 0.15. The standard deviation we're going to enter is sigma sub p hat, which is the square root of pq over n. So in this case, the square root of 0.15, q would be 1 minus p, right? 1 minus 0.15, which is 0.85. And n is our sample size of 1250. So let's pop that into the calculator. We've got square root 0.15 times 0.85 divided by 1250. That comes out to about 0.0101. So we're going to use the normal distribution with a mean of 0.15, and a standard deviation of 0.0101. Oh, and by the way, I forgot to change this in the notes because I made that mistake. We should have put the 1250 first, and then the 0.15 when we were doing the binomial. But this one I'm sure is correct. I know that the mean comes first when you're using the normal distribution. Okay, what we want here is the probability that p hat is less than or equal to 13.2%. But we have to put that in as a decimal, so make sure to change it to a decimal. So we want probability p hat is less than or equal to 0.132. Which means in the normal distribution, for the min, we're going to put negative infinity. And for the max, we're going to put in 0.132. And let's see what we get. So we've got 0.15, 0.0101. Let me just hide this one. Normal dist, 0.15 for the mean, 0.0101 for the standard deviation. I'll zoom in on that. Find the cumulative probability. I'm going to leave the mean at negative infinity, and we'll set the max to, oh shoot, what was it? 0.132. Okay. Okay. And you'll notice that we get a similar probability. Okay. It's not exactly the same, but it's close to what we got when we did this with the binomial distribution. Right, so this comes out to approximately 0.0374. Okay, so close, right? If you rounded to 2 decimal places, they would be the same, right? The same probability. What I would point out about these problems is that, it might seem a little bit silly because we already know how to compute probabilities with the binomial distribution, and using the normal distribution to do the same thing may seem like, well, why would you do that? And there's not really a great answer to that. The answer is this. You can follow this link. Oh, maybe not. Maybe I can't when I'm in edit mode, but I'll let you click that link yourself. And it's if you know the musical Fiddler on the Roof, then you'll understand, right? It's just tradition, right? It's just tradition. It's because binomial distributions, before the days of computers, all of these calculations would have to be done by hand. And so people made charts, right, where they had all of these charts full of probabilities that you could just look up the probability in charts. And it's easier to make those for the normal distribution than it is for the binomial. The binomial is a little bit more complicated when you're trying to lay out the possible values in a chart. And that basically is the reason why we do this. If I had my way, we would skip this, right? We would just use the binomial. But it's standard practice to use the normal approximation, and so I have to teach it to you because that's what you're going to encounter in the real world is people using the normal distribution to calculate these kinds of probabilities. And I would say, it is a pretty amazing fact that p hat is normally distributed, as I've already kind of gushed over. Let me just give you one more example. Okay, number 6 here says, an economist read that 67% of people oppose replacing $1 bills with $1 coins. She thinks that this percentage is actually larger, so she decides to take a random sample of 80 people and ask whether they are in favor of this proposal. If 75% of the people in this sample say that they are opposed, does the economist have good evidence that more than 67% of people are opposed? Well, to see if the economist has good evidence, we would want to compute the probability that she would get the 75% that she observed in her sample, assuming that this is the real probability, that 67% is the real probability. So that's what we'll do. So we'll assume, since we're computing a probability about a sample proportion, right, 75%, we will use the normal distribution for this. When we do, we need to enter something for the mean, right? Mu sub p hat is just going to be p, which is 67%. Sigma sub p hat is going to be the square root of p times q over n. So that's 0.67 times 0.33 divided by our sample size. This was a random sample of 80 people. Okay. And let's see about how much that is. I don't know why my decimal places disappeared just then. But so we'll do square root of 0.67 times 0.33 divided by 80. That comes out to about 0.053. Okay, so we'll use the normal distribution with mean 0.67 and standard deviation 0.053. And what we want to know is, well, what's the probability that you would obtain a random sample with a sample proportion of 75% or more? Because if that probability is really small, then we would say, oh yeah, like it seems like something is off here, right? And the thing that's off is probably the estimate that the economist read. Okay, to compute this probability, we're going to put as the minimum value 0.75, and as the maximum value, well, there's not going to be a maximum, so we'll type in infinity. Let's see what we get. So 0.67 and 0.053. Minimum value we said was 0.75. Maximum value is infinity. Let's zoom in. Okay, so that comes out to 0.0656. So to answer the question, does the economist have good evidence? Well, that depends. It depends on what you consider good evidence, right? If the standard, as we've talked about, is 5%. So if we had gotten a probability here that was less than 5%, then we would say, oh yes, this is unusual. And the reason that it's unusual is probably because this estimate is wrong, okay? But 0.0656 is not less than 5%. It's really close, right? So you could argue one way or the other, but I would say since 0.00656 is greater than 5%, we wouldn't call this unusual. In other words, if it really is the case that 67% of people are opposed, then you could reasonably get a sample proportion of 75% in your sample of 80 people. Okay? There's like almost a 7% chance of that happening, so it's not that unlikely. So we wouldn't call this unusual, and therefore the economist does not have great evidence. you know. But you could say, yeah, but it's still only a 6% chance or a 7% chance, right? So that is, you could argue either way, but that's what I would say there. Okay, one last thing that I want to do here is just run through a couple simulations just to show you how crazy it is, right? How crazy it is that that we get a normal distribution when we collect all of our sample proportions, right? That they end up forming a bell-shaped distribution. It's just so weird. Okay, so let's run a distribution. The example here says 76% of Americans believe the state of moral values in the United States is getting worse. Use StatCrunch to describe the shape, center, and spread for samples of size 10 and then samples of size 60. Okay. So I'm going to close this out and let's take a look at binary distribution. What did we say the 76% was the sample proportion or the population proportion, so 0.76. Okay. Oh, I've got 2 decimal places there. Let me try again. Okay, so this is our binomial distribution, right? We've got 0 represents a failure and 1 represents a success. And so you can see that the bar representing 1 is taller than the bar representing 0 because the probability of success was 0.76. We were asked to simulate taking samples of size 10. If I do this one time, and then they compute the sample proportion and drop it down. That one actually ended up being exactly 50%, but I could do this over and over and over again. Right? We could do it again. And the idea is that down at the bottom, right, we're collecting all of the sample proportions, and we want to know what shape ends up occurring if we do this a bunch of times, like 1,000 times. And you can see, we could do it 10,000 times. But you can see that after, well, we've got over 11,000 trials. You can see in this case that this is a skewed left distribution. Okay, it's really not bell-shaped at all. Okay, and that's because that condition n times p times q needs to be bigger than 10. That's not going to hold with a sample size as small as 10. But if we make our sample size 60, okay, we can simulate taking 1,000 samples of size 60. Okay, now that's bell-shaped, right? Just like the central limit theorem for sample proportions predicts. Okay, so I'm not going to write any of that down. This has been a long lecture, but that was just to kind of convince you that the central limit theorem is true for sample proportions as well as for sample means. But that will do it for this lecture. Thank you for hanging in there, and I will check in with you in the next lecture.